today about the energetics of circuit elements. Of selected circuit elements. Remember yesterday I was talking about a battery and a perfect conductor in and followed by a resistor or a thin piece of wire. And if this were a perfect conductor, that is the sigma goes to infinity of this piece of wire, then there can be no electric field inside the wire. Okay, we know that. Because a finite electric field would dictate an infinite current, but that's not possible because the conductivity is infinite. Which means that there can be no charge gradient on the surface of this perfect conductor. So there can be charge, but there can be no charge gradient. So if this is a positive terminal of the battery, this positive charge will evenly distribute itself on the positive conductor. And this entire piece of wire, since it's a conductor, it's going to become an equipotential surface. Likewise, this negatively charged terminal will share its negative charge evenly on the surface of this piece of conductor. So there is no charge gradient, and you know that electric fields are produced by charge gradients. So yesterday I erroneously mentioned that there can be no charge on these wires. There can be charge, but there can be no charge gradient. The electric field, however, inside has to be zero. Here there is a charge gradient across this thin piece of wire, so a large electric field will be produced. And a large electric field will be produced here. And E dot dl will always be zero. Alright. Now I would like to talk about energetics of circuit elements. Yesterday I introduced a concept, this neat concept, this nifty concept of the Poynting vector. E crossed with B. And I figured out how we determined how this object determines the flow of energy. Remember that in this particular circuit there is no electric field inside, so there can be no electric field outside because of the boundary conditions we discussed yesterday. However, this positive charge is going to introduce a radially outward pointing field. Now, since current is flowing inside this circuit and J is pointing downwards inside this wire, there is going to be a magnetic field. That magnetic field is going to point outwards here and it's going to point inwards here. And the electric field is pointing outwards. So if I were to plot the Poynting vector here, the Poynting vector is pointing downwards here and it's pointing downwards here. It will point upwards here and it will point upwards here. So energy is flowing along the wire, along the axes of the wires inside the circuit. But this energy is not coming from the battery really. It is in a sense coming from the battery because the battery is producing charges which immediately redistribute themselves because of negative feedback. But the moment you make this circuit, you close the switch, the electric field is set up in an instance of time, and these Poynting vectors are also established instantaneously. So everything happens instantaneously at the speed of light. Remember, if this were an AC source and if I were to reverse the direction of the electric fields, the magnetic fields will also reverse the direction, and still you'll find out that the Poynting vectors are pointing away from the battery along the wires and into this resistor. So reverse the currents, which means reverse the battery, and reverse the electric fields. The magnetic fields will be reversed. So both electric and magnetic fields will reverse their direction, but still the Poynting vector is going to point in the downward direction here and up in the upward direction here. So this is a consistent mechanism of describing energy transfer in AC circuits as well. Alright? This is something you have to figure out on your own. So what I would like to start off with is the following example. I would like to talk about a capacitor, two parallel plates, and a piece of wire connecting the two plates, and a current coming in. Suppose this is a steady current I, it does not change with time. Okay, so this is steady. That requires a variable voltage source, because the current is going to diminish with time if the voltage source is fixed. But if I have a variable voltage source that adjusts itself, that delivers more charge per unit time, I can have a steady current in this configuration as well. Now what I would like, do you understand this point? We know that if a capacitor charges, the current is not constant. But if the variable voltage source dictates supplies a necessary amount of changing charge per unit time, I can keep the current steady. So suppose I have a steady source of current and it's charging the plates of the capacitor. What I would like to see, how does energy flow inside this circuit? Of course, this charge deposits on the positive plate. This plate becomes negative, and an electric field is set up, pointing in the upward direction. All right. Now, there is a current, there is an electric field. What I would like to find out is this electric field going to be constant with time? First question. It's not going to be constant because this charge is continuously dumping charge on this positive plate. So the positive plate charge is accruing, it's gathering here, and the negative charge is gathering here, so the electric field is gathering. I know that this electric field is given by sigma over epsilon naught. Now this is changing with time. Because charge is coming and it has nowhere to go. So it just deposits here. So charge is building up, so the electric field is changing with time. It's actually growing with time. Now, suppose this is the exact center of this capacitor, and I go out a radius r and I make a path. So I make a path in the exact middle of this capacitor of radius r. Now I would take some point on this path P. I can take any point I like because all of these points are going to be equivalent. What's the magnetic field at point P? Is there going to be a magnetic field at point P? I know there's going to be an electric field at point P. It's going to be uniform everywhere. Suppose this distance is small and the plates are really large. Is there going to be a magnetic field at point P? Then where is Ampere's Maxwell's displacement current? Will there be, there is an electric field, you know that. Is there a magnetic field? No? Why? So magnetic field hoga? Exactly. You use the proper form of Ampere's law. There is going to be a magnetic field, even though I take this point P, if this is the enclosing surface. There is no current through the surface, but there is no conduction current. There can be displacement current, which means that there can be changing electric field through this area. And there is a changing electric flux through this area. Hence, if I apply Ampere's law here, the proper form of it, B dotted with dl about this closed path that I have drawn, this equals mu naught times the current enclosed, that is the current piercing this surface, which is 0, plus mu naught times epsilon naught times the rate of change of electric flux through this surface, d by dt, E dotted with dA, through this open surface. So I have chosen a path and I have chosen a flat surface. Now I would like to find out the current through this surface. This is 0. Is the electric field 0? No, it's not 0 here. So in this area, there is some electric field, and above and beyond it is changing with time. So there is a changing electric flux. So this term will be non-zero. This term is non-zero, so the magnetic field is going to be non-zero. So if I look at the left hand side, B 2 pi r equals mu naught epsilon naught. Now the electric field is pointing in the upward direction. The area vectors are inside this area. The area inside the path is also pointing in the upward direction. So I can just take this, and the electric field is uniform anywhere. So I can take this area outside. The area is pi small r squared into dE by dt. So this is the magnetic field at point P. You divide this by 2 pi r, you get the magnetic field. So I have an electric field and I have a magnetic field. The magnetic field is given by mu naught epsilon naught r over 2 dE by dt. So there is a magnetic field too. What's the direction of this magnetic field? So let me redraw this path here. I've redrawn this path. This is some point P. Now B into 2 pi r, which means that I've traversed this path in this direction. And the area, if the area vector is pointing upwards, I have to traverse the path in this direction according to the right hand rule. So this is a small area element, dA pointing upwards, which means that I'm traversing the path in the manner shown. Now the electric field through this area is also pointing upwards, E. So when I look at the right hand side, I get E dotted with dA is positive, it's upwards. Alright. Now B dotted with dl integrated gives me B into 2 pi r. This is also a positive number. So if this is positive, this has to be positive. So the direction in which I traverse this path has to be the same as the direction of the magnetic field. This means that the magnetic field is really circular. It's curly. This is the magnetic field. So at different points it's going to change its direction, but it's going to remain tangential to the path shown. Now I have determined the magnetic field. I know what the electric field is inside the capacitor. I can determine what the Poynting vectors are. Now the electric field everywhere is pointing upwards, even though the magnetic field is changing its direction. It's along the tangent. So at each point I can calculate what the Poynting vector is. Remember, the word pointing is quite a beautiful phonetic construction because it's technically accurate as well. Now let's look at the Poynting vector here. E cross B. E upward, B into the plane of the paper, S points in this direction. S points in this direction. S. Let's look what happens here. E upward, B outward, S points in this direction. Here what's going to happen? E upward, B like this, S into the plane of the blackboard. S points inwards. Here, S is going to point outwards. So if I look at this path from the top, S around this circle is always pointing inwards, into the axis of the capacitor. S points inwards like this, S vectors. Which means that if I look at this diagram that I've drawn over there, I can redraw the diagram. Diagrams are always helpful. I can construct a hypothetical cylinder of radius small r. So this is just a hypothetical cylinder. The Poynting vectors are all pointing radially inwards on the surface of this cylinder. All the Poynting vectors are pointing radially inwards. They are all crushing upon the cylinder in a way. So energy is flowing into the capacitor. From outside, it's flowing into the capacitor. So when a steady current is flowing through the capacitor, it's charging the plates, which means that energy is going into the capacitor. It's coming in from somewhere, it's going into the capacitor. The capacitor is increasing its energy because the flow of energy is into the capacitor, it's inwards. Let's look at how much energy is going into the capacitor, into this hypothetical cylinder. So there's a volume of vacuum here. There's some volume here. We would like to see how much energy is dumping into this volume. Suppose this spacing between the capacitor plates is small l. Now, let's look at the magnitude of S. S is 1 over mu naught EV. E and V are always normal to one another. E, and what's B? B is simply given by this. Mu naught epsilon naught R over 2 dE by dt. So this is epsilon naught R over 2 E dE by dt. This is the magnitude of the Poynting vector at any point on this cylinder. Now if I would like to find out, so this is watts per meter square. If I would like to find out the total energy per unit time, the power that goes into this cylinder, I just multiply this S with the area through which this Poynting vector is piercing. That area is given by 2 pi r L. That's the surface area of this cylinder. So the Poynting vectors are coming into a surface, they are rushing into a surface. That surface area is 2 pi r L. That will give me the total energy per unit time that goes into this capacitor. So that's the power that goes into this capacitor, into this volume, inside the capacitor. So this turns out to be equal to epsilon naught pi r square L dE E dE by dt. This is the total power that's going in to this volume inside the capacitor. Where is that power going? Where is that energy going?
It is reached in the form of electric fields.
It is exactly, it's going into the electric field. The electric field is building up. That electric field harbors energy. It has energy in it. Okay? There's no motion taking place, there's no heating up that's taking place. So the energy is just dumping into the electric field, which means that this capacitor is acting like a spring that is extending with time. It stores elastic energy, it stores electric energy in this case. So we also know that the energy stored inside a capacitor is the energy density into the volume that we're talking about. Correct? But the energy density is given by half epsilon naught E squared. You also know this. So inside this volume there is an electric field capital E. Associated with that electric field there is an energy density. You multiply this with the volume of this surface of this cylinder, is pi r square L. Now let's look at the time rate of change of this energy. Everything is a constant here, it's only that this E depends upon time. So I get epsilon naught pi r square L E dE by dt. But this is simply equal to the power that we calculated from the Poynting vector concept. Correct? So this power is actually increasing its energy, and this is the energy density that we already know about. This is the energy inside the capacitor. It turns out to be the same as the power that is described by the Poynting vector. So the Poynting vector gives a consistent description of energy transfer inside capacitors as well. It's all making sense. Now the question that you might ask is, here I've equated the power to the time rate of change of the electric energy, but there's a magnetic field inside as well. The magnetic field also harbors energy. Why haven't I taken into account the magnetic energy inside this piece of object? Right? Do you understand the question? So you can already see a magnetic field inside this object. There is a magnetic field, a circular magnetic field. The magnetic field also carries some energy. So the magnetic energy density Um is given by B squared over 2 mu naught. So there is a magnetic field. Why haven't I included something like this, Um plus UE into the volume? Exactly, really nice, because the magnetic field is constant. Because this current is constant. See, this current is constant. The magnetic field here at this point is also dependent upon the current. It depends upon dE by dt. But dE by dt is 1 over epsilon naught times the time rate of change of charge divided by area. But this is I. This is I over epsilon naught A. So dE by dt is proportional to the current. But if the current remains constant, dE by dt remains constant. So even though E is changing with time, dE by dt is constant because of the constant current. So B, there exists a B, but it doesn't change with time. So when I take the time derivative of this energy, this magnetic field is immaterial. It does not cause any power coming into this capacitor. So everything is consistent, neat, rigorous here. Questions? So the Poynting vector is an important concept. Traditionally, when we talk about electromagnetic waves, this is the first time the Poynting vector is introduced to students, but the concept is more generic than electromagnetic waves. It applies to real circuits as well, to capacitors, to inductors, to simple wires connected to batteries. And it's proper description of how energy transfers inside a circuit. It describes that energy transfer is instantaneous because electric fields are set up instantaneously, the magnetic fields are set up instantaneously. It describes how energy is transferred in AC and DC circuits, for example. It does not use convoluted concepts of the change in potential energy as a charge moves across a circuit, because that's happening at the drift velocity, which is really slow. Now we've talked about capacitors in detail, and we've seen the energy stored inside a capacitor. So how did we derive this energy inside? We know that the energy of a capacitor is given by half CV squared. This is sometimes also written as Q squared over 2C. Alright, there are different ways of writing this energy. So now I'm going to talk a little bit about energy in a capacitor from two different perspectives. We've already seen one perspective, and what's the perspective that we've discovered? We've discovered that if I have a charged plate that carries a charge plus Q and another corresponding plate that carries a charge minus Q, and if I would like to deposit more charge on this, which means I would like to take some negative charge from here and bring it onto minus Q, so if I have a negative charge which is taken from this plate, for example, then there is an electric field on this charge, Fe, that acts in this direction. But then I would like to make this charge go onto a negative plate, so I'm increasing its potential energy, so I have to do external work. So the potential of this system without the charge is V And if I put in this charge and this additional small charge dq, the amount of extra work that I need to do, dw, external work is given by v dq, but v is given by q over c. So this is the amount of extra energy that I have to supply externally to deposit more charge on an already charged capacitor. This is how I'm building a capacitor. I'm gradually depositing charge on it, which means that I'm separating out the positive and negative charge. I have a neutral plate, so both plates are neutral. I extract a negative charge and deposit it here. Then when I would like to do the second negative charge, when I like to deposit a second electron, I have to do some work because I'm moving against the electric force. When I deposit a third electron, I have to do some extra work because I'm moving against this electric force. So external energy has to be supplied to keep these capacitors plates at a distance of small d. Alright, so I'm just separating out the charges. That requires energy. Because once I've separated out a tiny amount of charge, the additional charge that has to come against an electric field. So I have to do external work. That external work is given by this. And the total energy that goes in is just the integral of this. If this capacitor is charged up to capital Q, then this turns out to be Q square over 2C. So this is how I derive the energy stored inside the capacitor. And that's equal to the energy density times the volume inside the capacitor. So this was one approach. But there are other approaches as well. There's another approach. So what this approach conceptually entails is that I have two plates. They are already separated out by a certain distance. Let's call this distance L, because d confuses you with dq over the differential sign. Let's suppose this distance is L. I have two plates, distance L fixed. Now I am transferring charge against the electric field, and I'm building up charge so that the final charge is capital Q. And I see how much energy I have put in. All of that energy goes to the electric field inside the capacitor. And that energy is Q square over 2C or half CV squared. ये एक तरीका है. The second method is, let's talk about forces and mechanical motion. In terms of forces and mechanical motion. Alright, now suppose I have a positively charged plate. That has all of its charge already put on it, capital Q. Okay? And then I have a negatively charged plate. That carries a charge minus Q. And this negatively charged plate is really close to this positively charged plate. Remember, this is a positive charge, this is a negatively charged body. So ideally, the potential energy is minimized when both of these plates coalesce, when they are together, because of the attractive forces. So if I maintain a rigid capacitor in which the two plates are at a distance L, this means I'm working against the attraction. The potential energy must be higher. Just like a spring, the spring likes to be in its rest position. If it extends, its potential energy increases. It stores elastic energy, which is available for vibratory motion. Likewise, if I have a configuration of this, I have actually worked against the attractive force between the two charge plates. Okay. Now I would like to find out if this is the case and these plates are separated by some small distance x. What's the force on the blue plate? I would like to calculate the force F on the negatively charged plate. What is this force equal to? Just the magnitude. Right. So let us speak up, let you raise your hand as well so that everyone has an opportunity, but you're correct. What's the electric force on this negatively charged plate? How do I calculate forces? I'm not talking about, we're going there, but this is a formula that you might have remembered somehow. But what's the amount of force on the negatively charged plate? Abutav. What is Coulomb's law? Coulomb's law is from the archaic times. It's really difficult to calculate this from the Coulomb's law because what R's are you going to take? Okay. Exactly what you would like to do. You would like to find out what the electric field at this location X is due to this positively charged plate. Right? You like to calculate the electric field. And then you multiply it with the charge itself, Q. So the force is given by E into Q. Right? But what is the electric field here?
Potential across the plates divided by the distance between the plates.
Okay, so that's sigma over, is it sigma over epsilon naught or sigma over 2 epsilon naught here?
Sigma over epsilon.
What's the electric field here? What's the electric field inside this region? Sigma over 2 or sigma over epsilon naught? Whenever I have a capacitor and two plates, suppose this is a rigid capacitor, charge plus Q, charge minus Q, the electric field is sigma over epsilon naught, where sigma is Q over the area. So I'm supposing that these plates are really large. So what's the electric field here? Sigma over epsilon naught? What electric field should I place here? I should actually place sigma over 2 epsilon naught. Why? So this electric field is really sigma over 2 epsilon naught into Q. The reason is that when I'm calculating forces, I just place a charge in an electric field and I calculate the force on that charge that has been placed inside an electric field. Now here my test charge is this negatively charged plate. This is a large uniform field that is produced by this single positively charged plate, that is sigma over 2 epsilon naught. So if I just have a positively charged plate, a large one, which has a surface charge density sigma, then its electric field is going to be pointing outwards and is going to be uniform, and that electric field is just going to be sigma over 2 epsilon naught. Now at this point the electric field is sigma over 2 epsilon naught. At any point the electric field is going to be sigma over 2 epsilon naught. Now I place test charges, which is really a collection of some other charges. Now at each point I have a small amount of charge, dq. The force on this charge is dq into the field here. The force here is dq into the field here. Alright? Hence the total force on this negatively charged plate is going to be sigma over 2 epsilon naught into 2. So this factor of a half sneaks in quite neatly. It has to be described. It's not sigma over epsilon naught here. Even though the electric field, once the capacitor has been set up, is indeed sigma over epsilon naught. But here we have sigma over 2 epsilon naught. But sigma is just Q over A. So I have Q squared into over 2 epsilon naught A. So this is the force on the negatively charged plate. that force on this plate is in this direction. This is the internal force, the electric force. Now if I have to maintain a distance L, I have to move the negative plate outwards. I suppose the positively charged plate is fixed. I've clamped it. I'm just moving the negatively charged plate outwards. So it's moving against an electric force, which means that I have to provide some external force to it. If the motion is really slow, which means that this object does not accelerate, the amount of external force that I apply is a tiny little bit larger than the electric force, so that this object moves adiabatically, slowly, in a quasi-steady way, so that the final length separation L is reached. Then I have to apply an external force all the time that is given by this. That is slightly greater than this. In the limit, it's going to be equal to this. So the external work that I have to do, which means the external force that I have to apply, is given by Q square over 2 epsilon naught A times dx. This separation is x. As I integrate x from 0 to L. This turns out to be equal to Q square L 2 epsilon naught A. But epsilon naught A over L is just the capacitance. So this is Q squared over 2C. And this is the energy stored inside the capacitor, Q squared over 2C, which is the same as the result that we obtained from the other approach. This approach is the deposition of charges whose separation has been predetermined. This concept is the charge has already been built up and we are separating out the plates against the electric force. Both of these concepts are totally equivalent, and they tell us that these are the two ways of constructing this capacitor conceptually. Either have two plates that have a fixed distance and deposit charge on them, or have the charge fixed and separate out the plates against electric force. These are the two ways wherein we can build a capacitor, and they determine how the electric energy stored inside the capacitor builds up. Alright? Now let's talk about a little bit about, okay, now if I look at this potential energy here, just out of curiosity, the potential energy, I'm not putting in the factor E, is given by Q squared over 2C. If the separation of these plates is x, it's Q squared over 2 epsilon naught A into x, right? Now let's take the derivative of this, du by dx. That's going to be equal to Q squared over 2 epsilon naught A. Isn't this just the magnitude of the force that is acting on this negatively charged plate? Yes, it is. So if I use this concept that the force on a plate is given by minus du x by dx, then I'm totally allowed to do so. Once I know the electric potential energy stored inside a capacitor, I can calculate the force on a plate just using this expression. The negative sign here shows that the force is acting in a direction to decrease x. So the electric force, the internal force inside this system is acting in a direction so as it would like to decrease x. That's why we have this negative sign here. So this is an entirely general relationship. Whenever we have potential energies, we can calculate the associated forces by taking the derivative of the potential energy, the gradient of the potential energy, and negating it, we'll get the force. Alright? So the force can be calculated if we start from the potential energy. From the force we can calculate the potential energy. Both of these are converse and equivalent concepts. Now what about inductors? The energy stored inside inductors. So inside inductors, we already know that suppose I draw an inductor which has radius capital R, and this inductor is just a solenoid. Okay. Length L. The total number of turns is capital N. I know that when I connect a battery across it, a self-induced EMF is produced. That self-induced EMF is given by L di by dt. I know that. So the power that is delivered to this inductor would be given by the induced EMF into the current. Alright? Just as if you have a resistor, the power that goes into the resistor is the potential drop across the resistor into the current. The power that is delivered to a capacitor, if you look at this capacitor example, it will be given by the current into the voltage across it. Okay, you can work this out for yourself. The power through any device, any passive device, is given by the voltage across it into the current. Alright, now if this is my power that goes in, which could be a function of time, right? The power could change with time. This is in watts. This is given by Li di by dt. Now the total energy that is going into this inductor, it's magnetic in kind. Some energy has gone into this inductor. Alright? That energy is going to be given by Li di by dt, this power into dt integrated from some 0 to some other time t. This is the total power, total energy that goes into this capacitor. So once a current flows, this inductor is not heating up, it doesn't have any resistance, that's our assumption. So that energy is going in somewhere, because a changing current has a magnetic field. If the current changes, the magnetic field inside changes as well. So a magnetic field is being produced. So that energy must go somewhere. That's going into the magnetic field. And how much energy is being delivered to this inductor? That's given by this expression. Power. This is just Pt dt integrated from 0 to t. Now this becomes equal to Li di from 0 to t. Now I have to change the variables from t to I. So at time 0, I assume that my current is 0, and at time t, I assume that my current has gone up to capital I. So this is the current at time t, this is the current at time 0. So I just integrate this, I get half L capital I squared. So the energy stored inside an inductor is half Li squared. The energy stored inside a capacitor is half Cv squared. Now where is that energy going? Let's figure out where that energy is going. Which means that we would like to calculate the inductance and the current, and we would like to express this in terms of fields. This is a circular description. Let's express this energy that is going into a capacitor, into an inductor in terms of fields. Here we haven't used any fields so far, but we can use Faraday's law to convert these circuit concepts into fields. The fields is a more general concept, and that's what we learn in electromagnetism. So we have the energy stored inside an inductor is given by half Li squared. What is that energy in terms of magnetic fields? For that, we have to calculate the inductance. The inductance is something you've already determined, by the way. Let me do it again for you. It will give you a nice recourse of what we've already learned. We know that the induced EMF, its magnitude given by Faraday's law is d phi by dt. d phi magnetic by dt. Now this is d by dt of the magnetic field into the cross-sectional area, which is pi capital R squared. Now this B depends upon time because the current is changing with time. So I have pi R squared d by dt of B. Now B is mu naught capital N over L into I. Remember, I have a capital N here because I have N turns. Okay? Now this N goes out, I get N squared pi R squared mu naught over L di by dt. But this object here is defined as the inductance. So my inductance L is given by this. My L is mu naught N squared pi R squared over small l. This is my inductance. What about my total current? Now the magnetic field B is given by a current. So B equals mu naught capital N over L, small n, which is capital N over L into capital I. So the current at instant t is given by I, and this is the magnetic field at instant t. This is, at any instant if I have the current I, this will be the magnetic field inside the solenoid. Okay. From here I get I equals B L over mu naught N. This is my I. Now I have the energy inside an inductor that is half Li squared. My L is mu naught N squared pi R squared over L. And my I squared, the square of this object is B squared L squared mu squared N squared. The N squared conveniently goes away, a mu naught cancels out with the square, and L cancels out here, and I'm left with B squared over 2 mu naught into pi R squared L. But this is just the volume inside the inductor, pi R squared L. So the magnetic energy stored inside the inductor is given by this energy density. This is the energy per unit volume into the volume of the inductor. No doubt there will be some leakage of the magnetic field outside as well, but that's going to be really small. The field outside is going to be really small because it's spread out over a large distance, over a large area. Hence, this also gives us strength in our belief that the magnetic energy density um, small um, is given by B squared over 2 mu naught. Small ue is given by half epsilon naught E squared. The total energy in a volume of space is given by this density plus this density to the volume of that space. So electric fields and magnetic fields harbor energy. I'd like to write out this sentence. Fields harbor energy. They carry energy. They are energy, in other words. You can't distinguish between fields and energy. Whenever you have fields, they will have energy. And this is a more general concept, by the way, because when we talk about half CV square or Q square over 2C, it requires some charge. When electromagnetic waves are propagating in space, it's hard to define where the charge is. There's no charge, but there's an electric field and a magnetic field. So radiation can produce electric and magnetic fields, and nothing to do with charges in the close vicinity. There are some charges moving in far away which are producing those electric and magnetic fields. But even in volume of space where there are no charges, you can have energy. And that energy is harbored inside the electric and the magnetic fields. And these are the energy densities. There's energy inside the magnetic field and energy inside the electric field. Alright, let's take a 1 minute break before we continue. Suppose I have a capacitor. This has a charge plus Q, and this plate has a charge minus Q. This capacitor has a capacitance C, and the potential drop across these plates is, say, V naught. There's going to exist an electric field inside, right? That electric field is going to be given by Q over A, that is sigma over epsilon naught. So if this separation is small l, and if I were to plot versus x, the potential inside this system, the potential is maximum here and it's going to drop linearly to L. Okay? And the slope of this line is going to be given by Q over A epsilon naught, or E, right? This is the slope of this line. If this potential is V naught, this is going to be equal to V naught over L. So far, so good. There's charge on these plates, there's a potential difference across these plates, there's an electric field associated with it. And the potential drops with distance. Here the potential is at its datum level, it's 0. Here it's going to be 0 everywhere, here it's going to be 0. Whatever the datum level you choose. You can shift the entire graph up or down, it doesn't matter. Now what I would like to do, I would like to take the same capacitor say the same L, and inside this capacitor I'd like to place another metal plate. Now this is metallic, this is a conductor. So this length is L by 3, this length is L by 3, so the width of this plate is L by 3. So 1/3 of the volume I'm filling with this metal inside. Now this is an isolated capacitor, so the charge on these plates cannot run off anyway, it cannot leave. So the charge here remains plus Q, the charge here remains minus Q. Now what's going to happen to this? Will it acquire any charge? No, it's a neutral metal plate, so it has to remain neutral. The charge cannot fly off anywhere, it has to remain neutral. What's going to happen to the electric fields inside this region and the potentials? If I would like to plot the potential versus x in this landscape, what is this potential going to look like? Can you give it a shot? Can you give it a try? Sorry? 12/3 होगी ना ये. Remember, nothing is happening to the charges. The potential might change. You're not clamping the potential. It's not connected to a power source. The potential might change, but nothing is going to happen to the charges. They can't fly off anywhere, and no charge can come out of these plates. Is L/3. And will the potential go down to 0? So will it go down to 0 or not? Can you have the same length L and you have flat here? This means then this means the slope is going to change. Then how can it go down to 0? What's the electric field inside this plate? 0. In electrostatic kinetic there can be no electric field. So if I take a Gaussian surface like this, the electric field inside here is 0, the electric field inside here is 0. So the total charge enclosed by this volume, inside this volume has to be 0 by Gauss's law. So if this has some charge plus Q or plus Q dash, this will have a charge minus Q dash. So this is plus. Total charge on this surface is plus Q. A negative charge of the same amount is going to build up on the surface of this metal plate. So this charge is going to build up, it's going to be minus Q. And a positive charge of the same type, of the same magnitude is going to build up on this plate, which is plus Q. So this is minus Q plus Q, hence an electric field is going to be established. There's going to be no electric field inside the plates, but it's going to be inside this void. This electric field is going to be the same as this electric field here. Q over A epsilon naught, because Q hasn't changed. So the slope of the potential change of the potential is not going to change inside this region. Inside this region, the slope is going to be 0. The potential is going to remain fixed because it's an isopotential. But the slope is not going to change. So if I subdivide this into 3 regions, L/3, 2L/3 and L. From 0 to L/3, the slope is going to be the same E, then it's going to remain constant, then the slope is going to be the same E. But now you don't drop down to 0 because you have a flat region. And you can find out what the potential of this point is. Or the potential difference between these surfaces, between these plates, is going to reduce from V0. Now what I have is Q equals CV. If the potential is reduced for the same amount of charge, the capacitance goes up. So for this object in which you have a parallel plate capacitor and inside this capacitor you put in a piece of metal, the capacitance of this material, of this device is going to go up. So you can store more charge on it with the same potential. So by inserting different kinds of materials in between the plates of a capacitor, you can tune the capacitance if the capacitance goes up. But this is quite an unusual scheme because generally you don't put in metals inside capacitors, you put in insulators. And insulators are generally called dielectrics. It's just a fancy name. Now what I would like to do in the last 10 minutes is talk about dielectrics. I'm not going to do justice with this subject material because it's a vast field out there. positively charged plate and a negatively charged plate. This carries a charge plus Q, this carries a charge minus Q. And instead of having vacuum inside these plates, what I have now is an insulator like mica, plastic, water, toluene, barium titanate, strontium titanate, PZT, any one of these very popular dielectrics. Okay? Now this is an insulating material. So charges cannot flow. The conductivity is really large. So this material is made up of molecules. Okay? Now if I have a molecule and it's non-polar, what that means is a negatively charged cloud and a positively charged center. And the center of gravity of the negative charge coincides with the positive charge. So this molecule does not have a dipole moment. Does not have any P. There's no separation of the positive and negative charge. It's not a dipole. It's a zero polarity. It's not a dipole. However, if I place this inside an electric field, suppose this is the direction of the electric field, then this molecule, the electron cloud is more mobile, it's lighter. The protons are heavier. So this entire electron cloud can slightly skew itself and shift in the downward direction, in the direction of the electric field, of the electric force. The positive charge remains there, but the electronic cloud has slightly shifted, which means that the center of gravity of the negative charge does not coincide any longer with the positive charge. Hence, a dipole is going to be set up, P, small p. That small p is going to be equal to the separation, delta, and the charge Q. So an induced dipole moment is created, and this molecule can actually elongate. It can actually change its shape in response to electric field. This is what happened in liquid crystals that were used in those older calculator displays. You have molecules that could elongate upon the application of an electric field. Alright, you put an electric field in another direction, the molecules can actually twist. Because you know electric dipoles are going to experience a torque in the presence of an electric field. So this is an example of an induced dipole moment. And if I could like to model this, I would model this molecule as it was initially neutral, it still is neutral. But now there is a dipole has been set up, which means that there is a negative charge here and a positively charged here. This surface has become positively charged with respect to this surface. Right? Nothing is moving and the charges are not moving. They're not going out of the molecule. The molecule itself may move, no doubt, but there is charge separation inside the molecule. An induced dipole moment is set up. Some molecules are naturally polar. They have natural dipole moments, like water. If you take the example of water, negatively charged oxygen and a positively charged end of the molecule here. So there is a dipole moment, a natural dipole moment, which is given by this separation, okay, which can be determined from the bond length and this angle, which is 104 degrees. And the charge that has been built up on the oxygen and hydrogen atom because of the difference in electronegativities. Water is one of the most polar molecules. That's why it has a high boiling point, because its dielectric constant is high. Because of these dipolar forces, life exists. Otherwise water would have boiled really easily and we wouldn't have water on our planet. So there are polar, naturally occurring polar molecules. Electrolytes are polar molecules. But you can also induce dipole moments. Now what happens inside this dielectric is that if I just model this as two columns of molecules, even though this is an exaggeration, then in response to the applied electric field due to these capacitors, which is E naught, what's going to happen is that induced dipole moments are going to be created here. This will become negative, 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 positive, 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 positive. which means that this object might have an electric field inside. This conductor here cannot have an electric field inside because it's a conductor and it's in electrostatic conditions. But this object, this dielectric, can have an electric field inside because you have separate positive and negative charge. It's really difficult to calculate the electric field inside. It is difficult to do that because this is not a homogeneous material, it's not a liquid, these are layers of molecules. The electric field, for example, let's take the electric field at two different points. The electric field inside, if you just ignore these capacitor plates, the electric field here is going to be zero because it's equidistant with the positive and the negative charge. The electric field, however, here is going to point, here the electric field might point in this general direction because it's closer to positive charges. So the electric field can be pointing in all kinds of directions inside the dielectric, but nevertheless there can be an electric field. It can be non-uniform, but there can be electric field. That electric field is difficult to calculate because of the structure, the molecular structure, and how the crystalline network of this insulator is being built up, or what kind of amorphous structure it has. Difficult to calculate the electric fields. However, what we can tell is that this end will be at a different potential from this end. How do we know that? Let's look at this in the next lecture. So I would like to start here because I think I'll go really fast if I give this topic its due. So I'm going to postpone this this point to Tuesday's lecture. However, there's a homework due on Monday which actually builds upon some of these concepts. So I'm going to delay that homework as well. Alright? But there's going to be a quiz on Tuesday evening at 6:30 p.m. that will not deal with dielectrics but will deal with everything else. Alright? And the homework is probably due on Wednesday now. Anyway, I'm going to delay the homework a little bit. I'm going to spend another half an hour on this on Tuesday morning before I move on to electromagnetic waves. Alright, thanks a lot.